No, I think we should have most people here now at this stage. So again, hello and welcome everybody, and I hope you're all well today. Um, as I mentioned already, my name is Tracy, and on behalf of Dr. Valet and all the team at rap.ID, I would like to welcome you all to today's webinar. We thank you for your attendance in today's webinar, and we hope it will be very beneficial to you. So before we start, I would like to mention again that there is handouts attached, so you can have a look through the handouts. You might find some information there that would be of interest to you. And we will also have some polls throughout the webinar, and you will also get the opportunity to ask any questions that you may have. So just some information on the presenter, Dr. Oliver Valet. So he is the co-founder of rap.ID. His background is as a physical chemist, and he has over 17 years experience in the pharmaceutical industry. So I will now pass you on to Oliver. Thank you.
Thank you, Tracy, so much for this kind introduction, and thank you everybody for attending today's webinar. And yeah, let's just spend the first couple of minutes in a quick introductory about rap.ID for those of you who don't know the company. So rap.ID is producing instruments. So we were an instrument manufacturer, and we were also a contract testing service lab. So our instruments are pretty unique. We are the only company that has fused together Raman spectroscopy and laser-induced breakdown spectroscopy, which is shortened as LIBS, into one single instrument. And we've also combined this with a microscope. So that makes us very special. And of course, we were using this tool to provide contract testing services. We do this for over 600 different customers worldwide. We are pretty much focused on industrial forensics, which means we identify particles and try to find their root cause. And in the long term, well, midterm also, sometimes very quickly and efficient, we can eliminate the sources of the contamination, and this leads in the long run to a better quality product. A second range of instrument is the Layer Explorer, and here we control lubrication in prefillable syringes and cartridges, sometimes also in vials. And siliconization or lubrication is necessary for the plunger to move in the cylinder of a syringe. And so it's a critical quality aspect, and we were pretty much focused on quality or providing quality data in pharmaceutical applications or for pharmaceutical manufacturing science. The rap.ID group, we have started 4 years ago to have a small daughter company in Monmouth Junction, New Jersey. Both of our facilities have been inspected by the US FDA authorities. We passed with no 483, so we were pretty happy about that. And it also gives you some, should show how we understand how important quality is, how important data integrity is. And you look into if you look into our services and into our systems, you will find both demands accomplished. Besides our instrumentation and contract testing services, we provide training. And naturally, that training is around particles. And over the time, we have established a friendship with Roy Cheris. He is one of the co-authors of the USP 1790. And that became effective this year in August. And we will focus today very much on implementation of the USP 1790, but also on streamlining it. And so we're pretty happy to provide these training courses from the New Jersey side. And in conjunction with the PDA, which is the Parenteral Drug Association, we provide the training courses here in our lab in Europe. And that's typically biannually. One is in the beginning of the year and one is after that. But this is all organized by the PDA. Now, why do we need particle categorization, or that's already a definition that you also find now in the USP 1790 lifecycle, and it's the determination of the material and also leads to the criticality. That means the when it's called an extrinsic particle, that can be anything that is not really under good control, and so this has a high criticality level. When it's an inherent particle, for example, an agglomeration of a protein, then the criticality is considered low typically, and so that's why we need this type of categorization. One important category is the intrinsic particles, and that is mainly primary packaging materials, also excipients or processing equipment, and that's where we focus later on when we talk about the subcycles, the so-called subcycles, when we control the level of particles that we find in rubber stoppers, in primary packaging like the vial or the syringes, or maybe even through excipients.
Hi all, we have got our first poll. What type of particles do you usually deal with? Check all that applies to you. So it's organic particles like proteins, polymers, etc., or inorganic particles like inorganic salts or minerals, etc., or metallic particles like steel, aluminum, etc., or glass particles. And we have like 90 seconds to choose your options. Yeah. And we have the results of our polls here. And it seems that 65% of the people voted for organic particles, which means proteins and polymers. And the next highest was metallic particles with 45%, and the glass particles with 40%, and inorganic particles with 30%.
Thank you very much for your voting, and also to give us the chance and your peer group to see what is an industry standard. PDA, in name John Chabushnik, made these PDA surveys, and from a PDA survey in 2014, or let's say that was the year when he published the data, you see that the most common types of particles found during visual inspection is the rubber and elastomeric particles, followed by metal particles. A good portion, or the next would be product related, which can also be classified today as the inherent particles, and then there is to glass. So that's the least. Linden fibers also the least. So that's a little bit different, that ranking, from what we've seen previously. Now, when we look into particles, so you can also characterize, or let's say differentiate them into visible and subvisible particles, of course. And when we take a look back into data that we have prepared over the last couple of years, you see that when we look into the visible particles, we found that the majority is cellulose. Some good portion is still unidentified. And then we have some polyester and other stuff. But when we look into this portion here, that part of the cake is glass, silicon, and carbon. So in a summary, you could say that cellulose, polyester, and protein polyamide was the major contributions to particulate contamination that we've seen. And I believe we've identified in the last 17 years maybe roughly a million particles. Now, Roy and also John, of course, and Scott Aldrich, they gave us a good guideline on particle characterization and a particulate risk management life cycle. And we will now focus a little bit on it. I will explain how it works, and then we talk about numbers. That means numbers of rejects, and of course then assumptions that we've made, how many rejects you have, or that's of course dependent on your lot size or your total amount of your entire process, but that's like the general guideline. And when we follow that, we have the sampling and initial monitoring, and from that we can develop a short-term historical profile. This is also something what we do when we come, let's say, when you start an investigation, you would also look into historical particle profiles. And if they don't exist, we do this as a starting point of an investigation. But of course, when you look at the life cycle, that is the historical profile, or that's the basis where you start with. And that's interconnected somehow with the identification of particulate sources. So it's always the question, where does contamination come from? And then when you do this for some time, you can develop an initial alert level. Then you optimize your process. That means you have identified sources, and now you can eliminate this or that material, or you change this and that way you process things, and or maybe you establish a more critical guideline with your suppliers of primary packaging materials. And then you continue and monitor, and after some time you can then evaluate your alert and action levels, and then you were doing this as a cycle. So when we show this as a cycle, this is the visual inspection, and followed by 100% visual inspection, which is mandatory. You can evaluate or work on the rejects. Basically, in the rejects there is the information. So, but you can only gain it when you do classification and trending. And that there was a question up front, so we encourage every attendee to send us some questions, and we can prepare a little bit. Now, one of the question was that from Maya, that how do I train my or it's related to training, because it's about the standard sets that you need when you train your visual inspection operators. So that's in this part, that training, where you get standard test sets from, or standard training sets, and there were a few provider of those, and we've put them together on our on the USP 1790 webpage. And when you look into resources, that's where you find the manufacturer of training sets. So that should be around here. Here should be our resources. And here you find standards. So standards are made by, in Europe, it's MAS, Material Analytischer Service. It's in the US, it's Dan Berdovich with Micro Measurement Lab, Phoenix Imaging, and NIST has some standards. PAL is making some standards with Solo Hill. So these are the main providers of these standard sets. And the standard is then a standard when it's good characterized. So it's a single particle seeded into one of your containers, and that is characterized, it's blinded, and then you train the inspector with that standard set so that he can recognize that kind of particle. So that's in this part. And of course, over time, you will have your own training set, because when you do classification and trending, then you have your own sets of standards because some of the particles are typical to your process. So you use your own samples and use them as a standard set to train your operators. Now, if you have something your operator hasn't seen before, that's when it triggers the investigation. And then the question is, if it's a typical, then okay, book closed and it's investigated. But if it's atypical, you update your defect library. And that's also something where we work with. And so here the training begins again, because now you also update not only the defect library, but also updating your training set. And that has, of course, an impact on both the visual inspection and the followed classification and trending. Now, in order to do this or let's say, the other thing is, how do I do it? So it's the how-to that's important. And so Roy has staged the approach into different levels. In level 1, you just look at the closed container. You can use magnifiers or more light than usual, but you can start describing what you're seeing. In the second level, then you open the bottle and you extract it, and then you have a polarized light microscope, for example, to decide if it's shining or dark or bright. And in the third level, you can then really discriminate what the material is. Like you use spectroscopy to find out, is it really that kind of steel, or maybe is it a different kind of steel? Is it my tip cap? So that's what you do there. So in a combination, in a summary, it's particle characterization is needed to fulfill the USP 1790. And in the long term, it might help to mitigate the risk of contamination, of course. And if you exceed limits, so that means you have limits, and then if you exceed them, you can start investigations. Yeah. And of course, in order to train your personnel, you need standards, but also a defect library, so that you have a definition of what is a defect and how do you characterize it, and also in which category do I characterize that. So Shankar, I think it's time for a poll.
Yeah. Hi, we have got the second poll here. And do you apply a staged and sequenced approach on particle categorization? And we have like 2 options, and yes or no. And we got like a minute's time. And let's see the results now. And it seems that 72% of the people had voted yes, and 28 with no.
Okay, most of you are experienced. That's great. So I can now give you an overview about in feedback loops, or also called subcycles. And so it's the supplier quality, and that means if you do that, you need component testing and acceptance. Then it's also, it matters how do you prepare your components, maybe the API, how do you mix it, how do you prepare bulk, and so on. So, and of course, very important is the data integrity. Now, you've seen that before, and we will now focus on this part where it all starts. And let's imagine you were just starting building a library. And when you do so, you might look into 100% of your samples with the level 1. So you can use maybe the inverted microscope, or you just do the characterization and typing. But you might, take a picture of each reject that you have. So 100% of the rejects are looked at with the inverted microscope. Then this number goes down because you already see, okay, that's this one, that's that one. So there is, of course, a decline with the batches. So let's imagine that's the 3rd batch, that's the 5th production batch. So that number of really rejects that you look at with the inverted microscope and take pictures with is lowering pretty fast, because your operators already know what they're seeing. So here we reach about 40%, and maybe here we were at around 30%, and that's then when you can say, okay, here I can have my short-term historical profile, and that's it. There's also a certain number of particles that you isolate, and then a much lower number, that's the small bars here, that's the number of particles where you really do spectroscopy on. And when you do this for some time, you're a little bit later in that stage, so now you can start optimizing your process relating to particle generation sources. And so, yeah, maybe at batch 25 you were here and you have already lowered the number of rejects, but also you need less inverted microscopes or other means of identification, because your operator is trained. So he knows what he's doing, and with his with the tools that he have, maybe a magnifier, maybe the lighting, and he's able to discriminate the particle. And that's why we stage the particle defect typing approach, because you need about 4 minutes, maybe 1 to 4 minutes to do the visual inspection with or without the inverted microscope. Then at the second level, you need tools. Classically, and that's the classic approach, you have capillaries or needles and other means of isolation, and it takes up to 20 minutes until you have that on your filter, or not on a filter, on a coated glass slide, and then you put it into the 2 classic instruments, which is IR and SEM, and that takes maybe 20 minutes each when you were well trained. So in 40 minutes you have also the identification here. And let's assume you do this for 3,000 rejects in the first 30 batches. So you would spend up to 18 working days on the level 1 characterization, up to 18 working days with the capillaries and isolation tools, and another 16 days with the IR and SEM. And then, of course, you're ready to evaluate your alert and action levels, and you have your book ready. So how can we streamline this a little bit? Because tools are there, the technology is there. A faster approach is, after that initial characterization into defect categories, that you use for the isolation tools, or let's say, first of all, that you have a quick and versatile tool to take a picture in the bottle. It could be an inverted microscope, could be a USP microscope with some training, so you can have a good picture in a short time. And when this is accomplished and you have that picture, for example, See the fiber. Then you isolate the fiber with a tool that is very quick and efficient. And one quick and efficient tool to isolate particles is the so-called filtrate. And in 5 minutes you can have prepared a sample by means of vacuum filtration. You do this in a controlled and clean environment to avoid cross-contamination, and you can also use it for the more classic types of analysis like SEM, IR, even for ATR analysis. And when it's isolated, you have it, and you can use it for spectroscopy. Now, and I come to the spectroscopy later, there is a tool that we have developed that has Raman and LIBS and microscopy inside. So in 10 minutes, you could do the whole level 3, and level 2, the isolation part, that's done in 5 to 10 minutes, depending on the volume that you have. If it's really a small volume that you filter, you can have that done in 3 to 5 minutes. And what does it mean in time? So when you have 3,000 rejects to work on, you lower the number of days. Well, you still work 18 days on the level 1, but you just need half of the days for the isolation part, and a quarter and only a tenth of the days with working with the SPE, because it's a fully automated instrument. So in total, you were 50% faster. And now it's time for our poll.
So we are here with our third poll. And have you established action and alert levels based particle types data? Is it yes or no? And we could have 30 seconds to answer this. So we have like another 5 seconds. So please, people who haven't voted, you could vote now. And we'll see the results now. So majority of people, like 58% is with no and 42% is with yes.
Yeah, that's half-half. Very good. So I continue and explain a little bit what it is, this staged approach, with some pictures and examples. So in the level 1, we use the inverted microscope, and I will now show some examples what you can do with it. All of you will know the black and white background. And with the black and white background, you can start to characterize your sample in a way that you are having maybe a spreadsheet, something like this. So what you can do is you start with the position. Do you find it floating in the solution, or is it adjacent maybe to the wall? So if it's floating in solution, you can select that. Now, the next thing that you might see with the naked eyes, if you're really good trained, it's the shape or even the color. But what you will see for sure is the buoyancy. Does it go up after swirling? Is it staying where it is? Like, has it a neutral buoyancy, or does it sink down maybe even fast? So if it sinks, you might see it sinking. Then here you might use different tools like an inverted microscope, and with that, or that USP microscope, and with that you see more. So you get a good magnification of that flake-like particle. You can already get a good idea about the size of the particle. You can, because the light comes from the back, it's you see if it's transparent, translucent, or even if it's flaky. And when it's looking like this, I guess everybody of you will know what it is. So it's fast sinking and it's transparent. It has this trigonal shape, so that's a glass. And that's maybe more some plastic type. This is how metal looks like. It's metallic, shining, and that's a lint or a fiber that is pretty straight. So with an inverted microscope, you can get really good pictures for your defect library, and it also helps you to train your operators properly. When we now go to the next level, and that's the filtrate or other means, then you first of all you need a clean bench. That's a controlled environment. We go into the clean bench only with sleeves and with gloves, and the gloves are controlled, powder-free. You can use these tools here, capillaries or needles, or and you put them onto these gold slides, for example, or you use the already explained filtration by means of this filtrate. Yeah, and then you use a polarized light microscope. And yeah, maybe we do poll number 4, Shankar.
Yeah, we are here with the poll number 4. What type of methods do you currently use for particulate matter identification? So you could check that all applies to you. And we have melting point and pyrolysis, polarized light microscopy, LIPS, which is laser-induced breakdown spectroscopy, molecular spectroscopy like infrared, Raman, or UV or visible spectroscopy, and atomic analysis, LIPS or EDX or XRF. And we'll have 60 seconds to vote this. We have got 15 seconds, and if you have not voted, please use this time to vote. And we'll see the results now. Yeah, and we have got, wow, molecular spectroscopy with 88%, that's the one with highest, and the next highest is with polarized light microscopy with 65%, and then atomic analysis with 29%, and LIPS with 24%, and melting point and pyrolysis is the least with 6%.
Yes, here are the experts, like 80% use. Yes, here are the experts, like 80% use molecular spectroscopy. That's great. And yeah, that's also what we were now look into mostly. The other tools are sometimes useful because molecular spectroscopy has some weak spots like fluorescence or high absorption. Sometimes materials start to burn. But in general, it's a great tool. And when we look into this, there are the more, I already mentioned this, the more classic types like the EDS and the IR, or the more modern, faster ones like LIBS and Raman. In a complete lab, I think you might want to have everything. We believe that LIPS and Raman is it's really fast to provide some answers. If you want to dig deeper, maybe you still initiate an EDS analysis, or if it really fluoresces, you might go to the IR. But when it comes to speed, I think these two methods, like LIPS and Raman, are pretty fast. We train also in the training courses IR and ATR. Here in Berlin we have mainly Bruker instruments, so it's the Bruker IR, ATR, and also the Bruker SEM EDS system. In the instrument, or in the single particle explorer as we name it, we have a combination of microscopy, so the instrument counts the particle, gives the particle size distribution, and it automatically does Raman spectroscopy and or LIBS. So it's an emission spectroscopy. LIBS in a nutshell is a laser pulse, and from that laser pulse we get emission that is telling us what kind of elements we have there. With the Raman we see structure because it's a molecular spectroscopy. Now just a few examples. This is on the filtrate. So here you see the pores in the background. That's a reddish type of particle. You see silicon, aluminum, calcium emission, and with the Raman we have ID'd it as quartz. It's a strong quartz or / sand peak. Plastic materials can have inorganic fillers. That's what you see here. There's some titanium, copper, and even some sodium on it. And with the Raman, we see clearly the polyester bands here and some titanium dioxide peaks there. So that's good to discriminate that plastic material from, for example, rust. It's an iron oxide. That's what you see here. And with the emission spectroscopy, the LIBS tells us that it's iron. The stainless steel, on the other hand, doesn't give any Raman signals. So the Raman is a flat line here. Basically some instrument noise, what you were seeing. Emission tells us it's steel, so it's clear that it's stainless steel. And that leads us to the next poll.
And how often do you identify particles by means of spectroscopy? So is it 1 to 3 times a year, or 10 times, or 50 investigations, or more than 100 investigations a year? And we have like 60 seconds to answer this. The majority is with 50 investigations per year, and there are two groups that voted like 10 times and more than 100 with 24%, and 1 to 3 times per year is with 18%. And we'll continue the presentation now.
Okay, 50 times per year do you make that investigation? So that's half of you at least does that 50 times a year. Most of you not that often. So yeah, I can just encourage you, do more investigations, you learn more about your processes. But yeah, I will give you a few examples now on single particle investigations, and then we go and concentrate on these subcycles. So when we make that defect library, that's typically the whole range of instrumentation that we apply to the sample. It's also what you can expect from us to get when you have when you use as a contract testing laboratory and you send us a sample. We do this in situ documentation, we do filtration, and then Raman, IR, LIBS, SEM, whatever is necessary to really give you a good result. And so one example could be that you have something like this. The operator saw something floating there. We suspect it's a hair, so it's a more critical type of particle. That's the object or the fiber on the after filtration. So you see some subvisible particles, but that's really the fiber that was seen. It's 2.5 millimeters in size. And when we are doing the molecular spectroscopy, that is what we get from the IR. And that's what we get from the Raman, from the SPE. That's the keratin That's the amide 1, 2, and 3 band. Same thing here. And so with both methods, we can say that this is a protein. And so that's the hair is confirmed that it's really hair. Now this is another one. It's a so-called stopper suspect. That particles was at least at the edges. It did transmit some light here. That's what you see. When we put that onto the filter, it looked different. It was red all of a sudden. And then when we hit it with the SPE, we get the silicon plus some titanium dioxide. And the same with the IR. The LIBS is not very specific, or we see some sodium, a little bit of silicon, some iron, which was also confirmed then with the SEM. And so that's the full characterization, what you can do with that kind of defect. The third category, which is pretty common, is a glass particle. This is how it looked in the closed container. That's the microphotograph, in situ microphotograph, and that is what we get on the filter. And this is what the single particle explorer tells us. So that is what the instrument does. It scans an area of 5 by 5 millimeters. That's where all the particles are. And this is the large visible particle, and it was in total 1.2 millimeters. And when you hit it with the Raman and the lips, you get a really nice, distinct lip signal, which is glass. We see a sodium peak here and some silicon and aluminum peak there. And that's what we get as the molecular structure with the Raman. Last but not least, this is a cellulose suspect at level 1. When you use the inverted microscope, you already see the structure, and with some training you know that this is cellulose. That's then the isolated particle, and when you hit it with the Raman, that's a clear one, so the cellulose with the match quality. And sometimes you have intrinsic particles, inherent particles that are suspects of agglomeration in your protein product. With the iPhone or the naked eye, they look a little bit whitish, translucent. And when you do the in situ microphotograph, you see that they're transparent and that they more appear like a bag, like a plastic bag filled with water. And we have a tool at hand where we can do in situ Raman spectroscopy. So we preserve the structure of the proteinaceous particle. And when we hit it with the laser, it reveals that it's a good portion of it is silicon. This is the peaks at 500 and 700, and this is protein related. That is something that sometimes happens with pre-filled syringes, and that's a good reason to look into the silicon levels that you have in your syringes. And that brings us straight to poll number 6.
And the poll number 6 is, and how long do you wait for your particle identification results? So is it like 4 hours or 4 days, 2 weeks or 4 weeks? And we have got 30 seconds to answer this. And we will see the results now. And majority of the people wait at least 4 days to get the results, and nearly equally 31% of the people voted for 4 hours and 2 weeks. That's with 31%, and 13% of the people wait 4 weeks to get the results.
Okay, yeah, that's a good overview over how long you wait, and I believe the faster you have the results, the more efficient is the root cause investigation, and you can do something against it. Once one of our customers and our clients said to me, you know, when I wait 4 weeks for a result, then the problem is gone. So yeah, that's sometimes the case. Sometimes we also see that yeah, it's the same stuff every time. So that's maybe a different story. Now let's take a look at an example that we have from another case where we had, or not we, the customer, the client had over time a lot of trouble with one sample. Or with one product, because there were several batches were failing in a row. And that brings us to filling and in-process testing, because that's what we did then in order to get to the root cause and to find out where the problem was coming from. And it's called a cellulose case study, because we went into the different we went more and more upstream in our investigations. And the case was starting like this. Customer came to us and they had 4 batches that failed in a row, and 3 samples of each of the failed batches were investigated. And also some of the good batches, because that's, if you remember, that's the historic profile of particles. And so we would have both, like the historic data and the current problems that we look at. And what we've seen is that it was very obvious that the cellulose played the major role in this type of contamination. And we could even say that the cellulose we were looking for did us a favor, because it had an extra peak. It was this peak at 1600 that you see here, and that makes that cellulose special. The other cellulose, like this one here, doesn't have anything going on in this region. So that's really a good marker to say it's this kind of cellulose that we were looking for. And so there were also samples from the filling were taken, and we had samples before a tubing rinse, before and after tubing rinse, before CIP, after CIP, and we had stoppers. And when we looked at those filters, we saw the stopper had 1 or 2 fibers. We've seen some of the contaminants, but only after or only before the cleaning in place and not after. And here it was the same with the tubing. And another important factor was, or let's say what we do next is, we built a library with fiber-like materials that the customer believes it's cellulose or cellulose related. And so we had here the autoclavation bag in blue, the inside, the outside, autoclavation paper, another blue bag. We had some paper, we had a sock, a t-shirt, towels, papers, trousers. And that was all built into a library. And then we looked into the product, into the tube rinse, for example, result. And what we found is we can now say, okay, is this cellulose that has something to do with the AC bag, or that cellulose that matches the paper towel, but it was all not the right contaminant. So what we did is we went upstream. So we really went upstream to find out maybe it's not in the filling environment, so it must be somewhere upstream. And here we found it. So we had a strike, and the samples from the API tanks showed the contaminant. And here it's a very clear thing. So 18 larger 15, 50, 5 larger 100. So that was how we connected the contamination that was found in the failed batches with some contamination in the API production. And so when we looked and updated the library, it was clear that it came from these type of towels that were used there to wipe down the tank. So when we conclude these cases, we can see that we had luck because it was one special type of cellulose. And so we could pinpoint this and find the source and eliminate the source, of course. But here, this was in a case of emergency. What I want to tell you is that it makes sense to do this before something happens, because if you have already a well-defined library that shows what you were doing or the processes and materials that you use in your production environment. And on the other hand, when you have looked into historical samples, then you would see that something has changed over time. And you might even see it before it becomes visible when you also look into the subvisible fraction. And that brings us to the next poll.
And we are here with our next poll. It's poll number 7. And yeah, in subcycle, do you control particle levels in elastomers like stoppers and pistons, containers like syringes and vials, CIP cleaning in place rinse samples, or in transport containers like bags, trays, and isolated ports, or it could be from APIs and excipients. So we have like 60 seconds to choose from. And it's time to see the results now. And we see that majority of the contamination sources are from containers like cylinders and vials, and next highest is from elastomers like stoppers and pistons, and APAs and excipients with 11%, and transport containers like bags, trays, and isolator ports with 6%, and it seems as no one has opted for CIPs. Well,
okay, that gives us a good overview. So I really thank you for your active contribution and helping us to make these webinars better and concentrate on what you're really interested in. Now, I'd like to compare two ISO methods in the final five minutes of the talk, and I'm very much tempted to make a special. A dedicated webinar on those two methods, because I think they are very important and very much discussed. Let's keep it that way. So the ISO 8871-3 is made for elastomeric parts, and so it's basically a test that was defined to measure the amount of particles that you can extract from stoppers. So let's take a look at the stopper example. The stoppers are a little bit special. It's a special material because the stopper is relatively vulnerable. So if you use harsh methods like ultrasonic cleaning or maybe too strong swirling, the rubber dissolves, sort of. Yeah, it falls apart, and so if you control particles, that's of course bad. And so the ISO method, the 8871, is defined in a way that you add an amount of stoppers into an Erlenmeyer flask, and then you use a detergent, mild detergent like Tween, and swirl it for some time. And that swirling motion is mild and gentle enough so to not destroy the rubber, but it's meant to remove particles from the stopper. And once you have all the particles removed, and that's not the question of this method, it's just defined like the amount of Tween, the amount of water, and maybe a little bit of the shaking time, but no one asks if that's really all the particles that you remove. And but after some time you stop the shaking, and then you just filter it, put it on a filter, put it in an instrument like the SPE, count it, and then you have a particle size distribution that looks maybe like this. So you have a lot of smaller particles between 5 and 10. You have about 6,000 here between 10 and 25. And you have only smaller portions between 25 and 50, and maybe none or two larger 50. And that's a typical result as you get it from these filters. You can use the filtrate in dark field mode. That is about twice as effective as counting the particles on a cellulose nitrate membrane. So just in case, if you wonder and compare numbers with filtrate and other methods, that's That's always twice effective. And that was a particle load from 25 stoppers. Then in the ISO method, it's defined that you calculate the particles per square or per area, in this example per square centimeter. So we know that 25 stoppers are 58 centimeters in square, and then you have a very obscure number. So that's the per 10 centimeters of square surface. So if you think about it, because I think the number per stoppers, it tells you more. In the end, you end up with two particles larger 50 micrometers per stopper as an average in this example. Now, what could that be, those particles I can extract from a stopper? And here we have some data, because we do this as a general and regular test. We've found some silicon, which is very likely because they were siliconized. We find some rubber, but we also find cellulose. And very often people tell me, well, I don't know where cellulose is coming from because we don't use it in our processes, but yeah, maybe not you, and others use it, and the silicon makes the stopper sticky, and the cellulose is then brought into the process. Okay, so I might continue with the stoppers, and from there on, I'd like to compare this with the other ISO, which is the ISO 16232. That comes from the automotive industry. There it's called the VDA, which is the Verband Deutsche Automobilindustrie, and it's cleanliness control. It comes from cleanliness control. It's made from engineers for engineers, and so it has some certain qualification steps built in. And it could lead us and help us to find answers to questions like this. Where could this come from? And this is what we have extracted. Most of you see that this is cellulose, and this is what we have extracted from a container. In this case, it was a bag that was used later on for stoppers. So the bag, it's maybe not the stopper, but it's the bag that has a big impact on stopper quality in this case. And when you see that, the question is, how does this ISO work? So what is the difference between the 16232 and oh, not so bad. No, not so good, I mean. Yeah, I will continue now because we might have a good recording, and I will provide the recording for you. Those of you who have trouble in hearing me, I apologize, and I just hang on and stick to it and finish this now. So in a nutshell, when I explain the ISO 16232, it's an extraction method, and it allows any kind of extraction, or it means physical force to remove particles from a surface. That could be rinsing, it could be swirling, it could also be spray cleaning or sonication. And this has to be defined for each component with a special geometry and, of course, material composition. So the material composition is important when you remember the elastomers, like the stoppers. If I use sonication on stoppers, they will dissolve and I will have some sort of stopper mass, but not the particles removed. So I need something that is appropriate for that kind of material. And when I have a strange geometry like a bag has, or maybe some types of containers, and I might consider having a spray cleaning to really reach all the parts in that container that are maybe hidden from me in the first place. And to do that, you do a qualification step. And the qualification is very simple. You just use the same method that you think is appropriate a second time on the same part. And then you should see less particles, because it's already cleaned, and you clean it a second time, so you should see less. If you see all the time the same number of particles, then something is wrong with your extraction process. And when you do so, and that is some data from Klaus Wormuth from Sartorius, and he showed that at the PDA particles and injectables this year, that is his extraction curve. And so when you extract the same part again and again, what you would expect is a declining number of particles, and that you also, after the fifth extraction with the same method, see that you have accumulated 10% or less than 10% of the total number of particles. And then the ISO says you're in control. So that means you can use that extraction method to extract particles from that part. And yeah, as I've already told you, I will then have a special webinar on the ISO, on the two ISOs for extraction. So let me conclude today's webinar with a claim from Roy Cheris, and he says the life cycle approach supports a product that is the definition of essentially free from particulates and defects forming, and that is forming the foundation of the USP 790 and also the USP 1790. We can try to make a Q&A session now, and maybe the audio is sufficient. You can use the chat function to ask questions. Yeah, Tracy, I hear you great.
Nee, also bis auf den Punkt, dass die Messung angefangen haben, haben wir jetzt nichts mehr gehört. Ja, das will ich auch.
Yes, we do so. We have done this in the past several times, and that's since the USP 1790 just became effective this year. Yes, we provide those trainings. In the US, we do this together with Roy Cheris. And here in Europe, we do it together with the PDA. And you find both like the upcoming shows, not shows, the upcoming trainings, you will find that in at the